Most often the question we are getting is which queue to use and when. Either it should be cloud based or it should be open source one. So this video is your quick guide on which messaging platform to use and when it is most appropriate to use which one. So basically the problem that queues or messaging solution they solve is, there are many actually. First of all, they address your performance issues, normal REST API calls, or resiliency is not there, durability is not there, your services start, maybe the call will get dropped, so you get more resiliency and you get durability, and of course you get scalability. And these days, of course, inter-microservice communication, you need basically service bus, or you need a queuing mechanism so that events can pass through. Thereby also you need to decide which queue to use. Thereby the people are often confused whether they want to go for RabbtiMQ or Kafka. So here we'll discuss which one to use, which one fits best based on your needs. There are 2-3 types of scenarios, first of all, that you have to think first based on your requirements. Whether you just have a simple point-to-point communication ordered queue where basically you are publishing one message from one side and you just have to consume it for other side. That queue is normally used when you have a buffering mechanism you want to add, or you have one service that want to wait for some events or some messages from the other service to process it in order. So that's a very simple point-to-point scenario. Another is publish and subscribe fan out, which is where you might want to do massive parallelism. For example, you want to have multiple consumers ahead, they want to do things in parallel. So this is a special type of queue which is called a fan out queue. It's also called PubSub, where you have multiple subscribers to the events. It's an eventing system also. And then you have streaming type of scenario. It's a log based basically. Mostly Kafka fits in this scenario, where you have basically people pushing in the message, but you want logs also to be generated for those events. In point number 1 and 2, logs is not the focus. These are the primary 3 scenarios for the messaging. Now the solution, if you go for the cloud in AWS and Azure, other clouds like DigitalOcean and Google Cloud, they also follow the same pattern of AWS and Azure. You have AWS SQS, NSS, and event bridge, and in Azure you have service bus, event verbs, queue storage. In open source you have a number of options, same technology basically, but in the open source version, Kafka, RabbtiMQ, Active MQ, NATS, and BullMQ. We'll be talking about those. So managed services are good because you don't have to do anything, they manage everything for you. And then they have all the alternative options available for based on your scenarios. If you have your PubSub, AWS SNS is good. If you have just a point-to-point, SQS is great. It is fully scalable, self-managed. And if you need event routing, you can use event bridge from the AWS. Same number of options you have. If you have streaming scenarios, Azure Event Hubs is a great solution. Service Bus is good for the P2P or PubSub. Queue storage is good only for the point-to-point going. So these are cloud options. When it comes to the open source, you have number of options from open source. You have Active MQ, Apache Active MQ. This is great P2P queue, and it allows a message broker also. So you can do a fan out also, as we discussed earlier. RabbtiMQ is there. Similar to these are competing solution. One is Java based. RabbtiMQ is Erlang based. RabbtiMQ is a bit more faster than Apache MQ, but if your ecosystem is totally based on Java, you might want to use Apache Active MQ. Then Apache Kafka is there, which is basically the granddaddy of all of these things. It gives you a lot more benefit beyond the other queues, but then there is a challenge in configuration and all those things, and sometimes it's an overkill, and sometimes it can be slower also, because of its head of line blocking thing that you need to be considerate of. And then you have this NATS, which is basically ultra low latency thing. This is extremely fast performing queues for the C++ or Rust world. Then you have BullMQ for the Node.js world. It's something that builds on basically Redis. It uses the Redis underlying technology to build a queue on top of it. So it's a very good and very fast in-memory queue. Now the decision making, because we talked about number of options, which one to use, especially the open source version, they are highly confusing. So this here we will discuss which one to use when. First of all, when you are deciding which one to use, you have to jot down all your requirements. You have to first think whether you are making the solution for a FinTech, or it's just that you are making a normal point-to-point queue where the events are lost. It doesn't matter how important is the delivery. There are number of semantics for the delivery, like at most once, at least once, or idempotency, like duplication of events should not happen, concept of transactions. So it's a basically complete world in itself, but we'll try to cap it in this video as much as possible so that you can easily make the decision before doing the unlimited R&D. So task queue focus, you need to process exactly once, reliably, durably, and at scale. These are the options. So self-hosted RabbtiMQ, Apache MQ is good enough. If you just need a queue, no logging is needed. You just need once only delivery, and you need the heuristics, like if the message failed to process on the recipient end, it should be redelivered again. These are the details that come up when you start to use the queues. So these are RabbtiMQ and Apache Active MQ both give you this feature. If in case the delivery is not successful or a message could not be processed successfully, both of these queues give you that option. On the cloud also, and the BullMQ, as I mentioned, these are nothing but basically a library developed on top of Redis and Redis caching. Redis is basically a cache solution. It's an in-memory, very fast cache solution. So they build a queue on top of that. So it's just a JavaScript and TypeScript libraries basically. Bull is very plain one. It allows some retries. BullMQ develop more on top of that. It gives you more feature like DLQ also. So, but again, this is JavaScript and TypeScript libraries on top of basically base infrastructure of Redis. So on contrary to that, RabbtiMQ is a comprehensive solution. It has a GUI and all those things whereby you can monitor things also, configure things also. So it's a comprehensive solution, and same goes for the Apache Active MQ also. This is a comprehensive solution whereby you have a complete web UI on how you can configure the queues, and these are also highly scalable solutions. Decision tree again. So basically you go for NATs if you need ultra low latency, very fast. Normally when you have, for example, a requirement in the C++ or Rust side, this is only good there. You have RabbtiMQ, which is also good for the massive parallelism. If your number of consumers are high, RabbtiMQ is a great solution. And then if you go for cloud, if your already solution is hosted on the cloud, then AWS good. Remember that when your solution is on cloud, you would always prefer to use the same provider, because then you want the traffic to be within the VPC, and you want the traffic to have as low a latency as possible, and that is only good enough when you use the service from the same provider. So if you have, for example, half of your solution in Azure and you're going to use the queue from the AWS, that is definitely going to be slower. So I have with me RabbtiMQ setup and the Kafka setup. I'll show you the exact semantic differences between the two. In fact, if you look at AWS SQS, NATs, or in fact Apache MQ, Active MQ, that is also similar to RabbtiMQ. And then you have Kafka. So if you understand the difference between the two, you will be able to easily decide which one to use when. So I'll start by RabbtiMQ because it's the simplest, most straightforward, and oftentimes is the straightforward solution to your backend microservice intercommunication. But that doesn't rule out Kafka. Kafka has its strengths, and it's very famous in FinTech world. Why it is the best solution in some of the cases, we'll discuss that also. So I have one RabbtiMQ instance. I have basically, as I mentioned, RabbtiMQ, one single instance. It gives you GUI also, one single Docker container you create, and you have the UI also built into it, and it gives you fan out, massive parallelism. So multiple consumers are running for the messages and reading it and reading them in a reliable way. That is all possible with RabbtiMQ. RabbtiMQ is based on Erlang. It is a bit faster than Apache MQ, but if your ecosystem is based on Java, you might want to go for Apache Active MQ. They both give you the similar functionality. They both have message broker where you want to have separate queues, and then you have multiple consumers, as I mentioned. So this is basically the RabbtiMQ, and I have here a simple queue with me. And in my test setup, basically, I have RabbtiMQ producer single, and then there is one container for the consumer. Consumer, I have basically two processes, two threads inside of it, running for the messages, because this is the benefit of RabbtiMQ. You have massive parallelism. Multiple consumers are trying to fetch the message from the queue. Within the queue, the messages are in order, but they can be fetched by consumers out of order also. So the ordering guarantee is not there at the time of fetching. That gives you a possibility of multiple processing, parallel processing, or fan out. And when it comes to selection of how you use the queue at the time of sending the messages in the RabbitMQ, the delivery and decision making is very straightforward. The only decision you have to take is about the persistent or non-persistent. It's very obvious. If it's non-persistent, it will be in memory, it will be faster. But then if you're basically the queue system, RabbitMQ crashes or your system crashes, you lose the message. Sometimes you want only the speed. The guarantee or the durability is not needed, but sometimes persistence is most. You want that message is there and it is redelivered if it's not consumed properly on the other end. By the way, non-persistent does not mean message will never be durable. Also, in the non-persistent case also, if during the process message is not properly processed, it will be redelivered also. But since if the machine of the RabbitMQ is gone, then you do not have persistent, the message is itself gone. Then in that case, durability will not be there in one of those cases. And at the consumer side also, the decision making is very straightforward. The only decision you have to take is auto acknowledge or manual acknowledge. The difference is at the time of fetching, you want to do immediately the acknowledging that you have received the message, so that queue can consider that message is gone and can delete it. So there is one aspect here, persistence. Either you use a persistent storage or not, the message is gone in these queues once it is delivered. This is the by default semantics. So storage concerns and all those storage planning is mostly not needed. At the same time, the downside is if the messages grow too much on the RabbitMQ, the throughput challenges come in. So that is the downside. However, the plus side is it's very efficient as a queue. It's very suitable for the normal inter-microservices communication. So talking about the manual and auto is you immediately send the acknowledgement that you have read the message. Manual is you want to control that acknowledgement. For example, it takes you like 5-10 minutes, you do some processing and then you do a manual commit that okay, I have done the processing of the message. The benefit will be just in case during the processing of the message your consumer crashes, so you will be able to have that message again in the next cycle, because RabbitMQ will consider that you have not really consumed the message. It will be sending you that message again, so you get some durability. So that is only two decisions you need, and RabbitMQ apart from that is very straightforward to use. And in terms of this container, I can show you I have a single producer here. I can spin up this container and my producer is up. So if you see, it has started sending the messages. All the messages are basically JSON based, 1 to infinite number of numbers, and you see it's now started to send the numbers. And if I spin up the container, as I showed you, basically there are two processes, and I showed you the configuration from the code. What they are doing is just consuming the message. They are racing for the messages, so there are two of them, so they are reading up the messages fast. So if I come to the queue configuration, as I mentioned, so you see my queue is here and it have 0 messages inside. For example, if I go here, because get messages, get one messages, queue is empty, because the messages are getting consumed as rapidly as they are getting produced. So you do not have the persistence, you do not store those messages, and the message is gone. But if in case I stop the consumer, for example, these are my two consumers, now they are no more listening to the messages. So if I come here and if I refresh my queue, suddenly my queue will start to grow. So you see, you have 3 messages here. If I go to the queue and I try to get message, you will get one of them. So the queue will start to grow. So this is the buffering mechanism you also get. So you can make use of it in many ways, like normal one-to-one pub/sub queue or ordered one-to-one queue. So this is very straightforward and good solution in that case. So now my queue will start to grow. All of a sudden you have 28 messages now in the queue. So if I spin up my consumer again, it will definitely, there are 2 consumers contrary to the single producer. So rapidly my queue will start to go down. So right now, for example, it's 39 messages, and If I, for example, refresh again, they are getting down at 24. So consumer will start to consume the message and messages will be gone. So most of the time, this is a straightforward solution. You can use Apache Active MQ also, which is more or less similar to it, little bit slower, but it gives you most of these features that RabbtiMQ gives you. Also, you can use NATS also, which is ultra low latency. It is very famous in the C++ and Rust world, where you need ultra low latency and very high speed performance, and all those aspects are very critical there. But definitely setup is little more complicated than RabbtiMQ, but it is a good solution. And plus it can give you persistent also if you use Jetstream with it. So these suite of solution, there is options from Azure also, as I mentioned earlier. So these type of queues are very good if you want a very lightweight broker and you want very lightweight handling and you do not have very storage planning also. You just want is a queue that gives you buffering and all those other fan out thing. Another very good advantage of these queues like RabbtiMQ, which is beneficial over even Kafka, is they give you massive parallelism. You have number of consumers, there is no head of line blocking. Like for example, one message is there which is at the top of the queue. It is going to take a lot of time. So that is, in the case of Kafka, is a blocker, because within a partition ordering is must. Unless that message is processed, the acknowledgement is not received, you cannot jump to the second message because it's offset based. But this queue, even you can delete the message in between. There is no concern of immutability. So it's rapidly faster and you can achieve massive parallelism also, no headline blocking. So sometime in some cases, although people know that Kafka is faster, the throughput is very high, but what people do not focus on is that RabbtiMQ can be faster in many cases in terms of, especially when the consumers are more. So this is a very beautiful solution. Now coming to the Kafka basically the decision making is little bit more. Then you have to basically on the producer side and on the consumer side, the parameters are more. And also the setup is little more complicated. However, it is a beautiful solution when it's a FinTech specifically, because by default, the first difference that comes from Kafka is it gives you persistence. All the messages by default in RabbtiMQ, they are not persisted. In Kafka, by default, all messages are 7-day retention is by default there. So they are there. Plus, it's like streaming. It's like Kafka, there is a statement, that is said, Kafka is a Netflix of data. Because as soon as you publish or stream new data, it's available to all the subscribers that are around. So basically, you have log stream type of thing where you would keep pushing in new thing, and people get the new information as it comes or as you push into the Kafka queues or partitions. So when it comes to Kafka, the decision making is immense actually, but it's not too scary either. But then you have to decide how to basically use it. So there are a number of different delivery options. Before I jump into that, I'll explain them. I'll just have a quick overview of comparison. So we talked about RabbtiMQ, which is similar to AWS SQS, and in fact similar to Bull and BullMQ. The only difference between Bull and BullMQ, they do not have a queue underneath. Basically, they use a Redis library only, so it's only totally in-memory solution also. There is no persistence. But in RabbtiMQ, it is a proper queue with the GUI and every management is possible. You can dynamically from the queue GUI itself create the queues. Plus, it gives you persistent option also. Plus, it gives a proper queue protocol, AQMP, which I'm going to discuss. Contrary to Bull and BullMQ, there is no protocol. It's just a straightforward queue. Especially in the Node.js world, these are very suitable because it's a code base is basically derived from the JavaScript or TypeScript. Then you have NATS also, which I mentioned earlier. So only downside for the Kafka is you have to beware of the head of line blocking, which we are going to discuss. Then there is a concept of DLQ. We haven't talked about DLQ a lot. DLQ is basically when you have a poison message. You have a message that you cannot process when you receive it. It's a message that is that you want to signal back the sender that the message you sent was something that is I'm not able to process. So you want not to just bypass that thing. You want to signal back your original sender, or you want to have some exceptional processing for that message. So that is called a DLQ, dead letter queue. You put that message in a separate queue, and that queue, some listener is there, either it's the original sender that can come to know, okay, I sent something that wasn't processable, or maybe you have some exceptional processing for that message. This is good for the payment processing, like payment could not through and you want to undo, or you have some special action in that case. And then of course each queue has a delivery semantics, as I mentioned, at most once, at least once, exactly once. This you need to plan for in advance. So these queues looks very simple, but when you get into the details, you will get to that. So we'll directly be jumping into idempotence. You will get to know when it is important and how to handle it. And persistent behavior, as I mentioned, it's enabled by default in Kafka. It's not so the case with the RabbtiMQ and the other queues. And the protocols are very straightforward. AQMP is the mostly used protocol. RabbtiMQ, Apache Active MQ by default gives you AQMP. On contrary, you have MQTT also is basically mostly binary form of data, mostly used in the IoT world. You do not have to use it. It's not by default enabled either. And there is a text version also, which is also not by default enabled and useful. You mostly land into AQMP. It's just knowing that these terms, and it's good enough. And then there is another concept of push or pull. RabbtiMQ is a push queue. Basically, it gives you the event when there is a message available. On contrary, Kafka, you basically have to have a subscriber, you keep listening. But that doesn't mean one thread or 100% CPU is wasted just because you're listening. The subscriber gives you a callback when you subscribe to it, but you have to subscribe. That's the pull semantics only. And the ordering guarantees. I mean, how does the queue ensure the ordering of the messages? So in RabbtiMQ, Apache Active MQ, per queue ordering is there. The order will be preserved in a FIFO in the order that the message are received. But in case of Kafka, only per partition ordering is there. This is something I'm going to explain so that you can come to know what exactly we are talking about here. So durability, persistent queues are there. This is a disk bake loss in Kafka. And other solution, they are all give you persistent queues. Replay capability is something fantastic which only Kafka gives you, if you notice, because Kafka is keeping a log of the message since the day one of the original message. No message is deleted, so it gives you a replay capability, which is in some of the cases very good. And the throughput, if you see, medium is for all, but it's very high only for the Kafka or NATS because it's ultra low latency. And for the Kafka, it's very high because it's meant to handle high amount of load. It's a log base. It's designed with a cluster in mind. Multiple partitions are there. So if you have a data or a queue where mostly the queue size is very high, Kafka is a solution because storage planning is there. Contrary to that, RabbtiMQ, when the queue size grows, it becomes slow. It's not a good solution. And the latency, of course, NATS is meant for the ultra low latency, so it wins in those cases. When you have ultra low latency requirement, then obviously NATS is the only solution. Other than that, Kafka and RabbtiMQ all are low. This is good enough. And then you have parallelism. Parallelism is an important topic because Kafka, it gives you, it's limited by partition, this parallelism, because within the partition ordering is there and then head of line blocking is there. Even if you have consumer groups concept in Kafka, multiple consumer running for the messages, but only one of them will be reading one only, because there is no concept of per message acknowledgement in Kafka, which is a limitation. By the way, there is a advancements and there is some planning going on to put this feature into Kafka also, because this is a limitation factor for Kafka where massive parallelism on the consumer side is not possible to date in Kafka. However, that is from the day one possible in RabbtiMQ, which is why I suggested that you can use it, especially when your consumers are more. Like, for example, you have one or more instances of your microservices, same microservice but multiple instances, want to do the processing in parallel. RabbtiMQ, they can read from the queue in parallel, and then they can boost up the overall parallelism of the overall system. Not so straightforward is the case with the Kafka, where you have to have as number of partitions also available within a single partition. That thing is not there. So security feature, they are almost the same. Basically in Kafka, you can have even ACLs also, which is a step ahead from others. Sometimes you need security, but sometimes when the things are within the same VPC, same network, same LAN, this is irrelevant. So based on some scenarios, it is needed. So all of them, they come in a managed service form also, and open source also. So in case of RabbtiMQ, you can use a open source RabbtiMQ. If you want a hosted one, you can use a Apache MQ Active MQ, which is more or less the same semantics, but it's based on Java. RabbtiMQ is based on Erlang, and both Azure and AWS provide you that. In case of Kafka, there is a service from Confluent, or you can use an open source version. You can spin up a Docker. I have one. I'm going to show you how it fits. Compliance, if you see, the high is with the Kafka, of course, and moderate with the RabbtiMQ, because RabbtiMQ in between the queue message can be deleted. Now, in case of FinTech, this is not desirable. In case of Kafka, you cannot do that. You play with the offsets, but you never play with the deletion of messages. If one bad message is there, even if you put that in the DL queue, the original message will always be there. Not so with the case with the RabbtiMQ. So that's another benefit you get with the Kafka, which is why it's very famous in the FinTech world. It gives you immutability also. No? So you get the logging benefit, and you have the replayability also. So last point is immutability, which I already mentioned, that you get the benefit in terms of Kafka, you get an edge over there. Now, when we come to the consumer side, as I mentioned, you have to first of all decide on the delivery strategies. There are 4 of them. By default, they are not by default all of them supported by the Kafka itself, by the way. So, but I have documented them. Some code is needed to develop them. So, in my case, for example, I have exactly one idempotence. This is one of the keys. In exactly one idempotence, the flow is you receive the message, you generate a unique message ID, you generate it from the queue of the partition, or by at the time of sending you do that, and you do you have a table in your database where you're checking if you, in case you have done the processing of that message within your system, you have a table where you have a unique IDs. It can be GUID or anything. Basically what happens is, when you're doing a transactional processing, at the end of the transaction, you add a special record in the dedupe table, which is a dedicated table to handle deduplication or handle idempotency, where you put in a special record which is one-to-one relation to the transaction, that this transaction is completed successfully. So basically, at the time of fetching of message, you check if the record is there. If in case it's not present, then you mean this transaction was not completed and it now can be completed. So you eventually achieve a idempotency effect. But remember that this is outside the scope of Kafka. I have done some coding here to show that how it is done, because mostly is needed, especially with the FinTech. Whenever you use Kafka, you have to build that code, and it's very necessary so that you don't end up handling a duplicate processing. There are many edge cases why that can happen. Duplication cases are many, because let's suppose, for example, you are doing processing on the, for example, Stripe payment gateway after you receive the message and your consumer crashes. Now you will going to receive the message again, because you could not tell the Kafka queue that you have done with the processing of the message. The message will be there again for you. You will end up sending the double payment. So that's only one scenario. Also, there are more scenarios why it can be case. Kafka can crash itself also during the giving you the message. Then again, it is going to give you the message. So there is not one. I have mentioned here many. You can read them later. There are many cases when you can end up having a duplicate processing. So idempotency is must, especially in case of FinTech. But that is not always the case. Sometime all you want is this strategy, at least once or at most once, where you only worried about performance. You are not worried about whether they are getting duplicated or not. Like for example, logging is there is no harm, for example, if you get the log message for something duplicated. So I'll come to this option number 2, but before that I want to explain you number 4 and number 3, because they are more easier and more relevant to number 1. So at least once manual commit is something, you do the processing similar to I explained in RabbtiMQ. They are exactly same. So in one of them, you immediately receive the message and you immediately acknowledge that I've received the message. So the Kafka can come to know that I've done with this message. I can send again the new message. This is to increase the speed and the performance. However, the double delivery is more eminent, and then you can run into different type of issues. The use case is mostly streaming. So basically, you do not want to hold the whole queue just because you are doing something, because what you are doing is not essential. And then manual commit is already explained in Kafka, where you want to have a more granular control of when you want the Kafka to know that you have done the processing with the queue. This third one is transaction. This transaction have nothing to do, by the way, with the database transaction. Transaction, you have a concept mostly in the databases, right? You do one operation and you roll back that operation if the operation was terminated in between. Like for example, a database engine crashed and you were in the middle of a transaction. So when the database engine will restart, it will look for any transaction that could not complete it. It will roll back the transaction. So it gives you atomic operations, which is very necessary in the fintech world or where you're using critical processing. Similarly, you have a concept of transaction in Kafka also. Basically, what happens is you have a batch of messages. One is you are sending a message to credit one account and you are sending a message to debit one account, but both have to be submitted together or none. Let's suppose if Kafka crashes, or for example, your producer crashes, you want to ensure that either the two messages are submitted in the queue as one, but it never be the case that only one is gone or submitted in the queue and the another one is not. So this adds a value to the fintech where you want to make sure whatever you're submitting the queue is also an atomic operation. So it gives you more control. So these transactions are inbuilt supported by Kafka. However, people confuse it with the database transaction. It have to do nothing with that. It's only with the producer part. It's only with the submission part of the queue where you want to ensure that whatever you're submitting is basically committed. But there is one small catch in that. At the time of reading, you have to set this special flag. Read uncommitted should be false. You only want to read committed ones, similar to the database concept. So read committed flag is something that you want to be aware of. Apart from that, other considerations are FIFO basically. Kafka, as I mentioned, it's built on partitions. If you look at the basic artifacts of Kafka now, there is a topic. Like channel, you have in the other world, you have topic here. Topic is the main headline name for the concept of the queue here. But within a topic, you have to decide on the partitions. So partition is something where basically ordered is maintained. You want it or not, this is a rigid limitation. So within a partition, messages are stored in order and they give you immutability. Within a partition, you cannot delete a message also. Within a partition, you have header line blocking also. So consumer group is the number of consumers that want to listen to the partition. So they are attached to the partition. And the replica is number of copies of the partition for the fault tolerance. See, this is something you want to additionally add in case of, for example, high availability or the data disaster recovery. So this is good in some of the cases. So partition is something that you have to design. The main Kafka design, when you do that, now you have to focus on partition because of head of line blocking. So apart from that, besides the delivery semantics, there is also an option for the compression strategy. It's a very comprehensive solution when it comes to, a proper solution for the queuing or for the fintech, immutability also, logging also. Kafka also topples RabbtiMQ. Also, there is only one downside when multiple consumers are there and head of line blocking is there. Apart from that, if it's a one-to-one mapping or even in some fan-out cases also, Kafka is the most best fit solution, especially in fintech where you want to keep a record of whatever is going around. And then you can select not just on the compression strategy, you can select on the encryption strategy, you can select on, even you can build up DLQ is by default not there, but you can easily build up that code also. So if there is a bad message in the queue, you can put that in a separate queue also in the Kafka. There is a very little code required to achieve that also. So these are the decision making. So if you see, the decision making is a little bit difficult, but it's not that big of a rocket science either. So in my simple producer for the Apache Kafka, I have a single thread basically who is just writing the same numbers as we were doing in case of RabbtiMQ, and it's just pushing the messages. In case of consumer, basically I have simply like for example, my simple consumer is here. It's also just doing nothing. From the same topic, I'm just reading the messages. So if I come to my containers, I can just put this whole thing down because you have seen the RabbtiMQ. I'll just spin up the producer for the Apache Kafka, and I'll spin up the consumer for the Kafka also. This is my Kafka by default. Also, one or more factors there. Kafka, it doesn't have a UI. You have to use your own UI. There are many open source available. I have used this one, Kafka UI, and you can use, there are others also, but this is more straightforward and a simpler one. And also Kafka setup is sometimes a little bit complex and complicated, especially when you have you want to use a very high throughput, like millions of messages per second. Then you have to have a cluster design, high availability, and all those considerations, because storage planning, as I mentioned, is also needed. 7-day retention mean if your millions of messages are going through, your drive is going to get full very, very soon. So you have to plan for that also. So we'll jump to the producer first. As you see, my queue was spin up, and I have at least once a delivery semantic here, and I have started to submit the message. As you see, numbers are growing because they are getting submitted in the queue. So if I come to the Kafka console, for example, this is my Kafka, and if I come to topics, you see there are two things. My topic is there where the messages are getting in, and you see number of messages 231. They will always be there for 7 days. After 7 days, they will start to get removed from there. And then there's a special queue, if you notice. This is the basically offset. So Kafka, as I mentioned, messages are not getting removed. All the consumer, their pointers are also maintained by Kafka itself. So whenever the consumer crashes or comes back again, Kafka knows where to resume it from. It's not the consumer that is maintaining the pointer, it's the Kafka that itself, it knows from the name of the consumer or how it registered that where to resume it from. So you can achieve all that exactly once, at least once, or at most one semantics, whichever is needed for you. So if I come here, I can see all the messages, all the JSON bodies are there. So this is another beauty of the Kafka. Messages are there, so auditing is there, immutability is there. So this adds to the fintech world. Sometime when the in the fintech world, when money is involved, this is of crucial importance. So similarly, if I come to my consumer side, on the producer, for example, or on the consumer side, I have a single thread here because, of course, if I have a multiple consumer, they will only be running into head of line issues. So I have a single consumer who is just using this as a queue in a FIFO way. There is one big question at the end of this. You have microservices architecture. You want to do the inter-microservice communication between all of them. Either you'll go for RabbtiMQ or you'll go for Kafka. Which one you will be choosing from? Can both fit the requirement? Are they both good for the inter-microservices communication? Yes. Yes, in the case when, for example, you want to have immutability and you want to have logging and you want to have scenarios where the queue is going to grow too long, and you can manage to have the storage also, and you can manage to have extra administration cost also, then Kafka basically complements and can totally replace RabbtiMQ. However, with only one downside of head of line blocking, where you want to achieve massive parallelism. So Kafka does, and Kafka is very famous in the banks and in fintech industry from this aspect. So you can entirely replace your RabbtiMQ for the inter-microservice communication bus when you have this scenario. Other than that, 99.9% of cases, RabbtiMQ, Apache MQ, Active MQ, or AWS SQS, or the similar solution from Azure, as I mentioned earlier in the presentation, are good enough. And the last, if you have a low latency and you have a replacement of RabbtiMQ that you need, NATS is a very good solution. And also, if you are in the Node.js world, if you do not want to have anything extra, no queuing, no AQMP protocol, you just want a simple MQ in memory only, and you do not care about the durability or the persistent message, Bull and Bull MQ are good solution. Bull is plain JavaScript. It doesn't give you any extra features like retry or DLK features. Bull MQ gives you that also. Thank you.